Okay, so we've been working on finding roots of polynomials, and we've talked about the rational root theorem by now. And I just want to share a really useful, um, helpful tool to help you find roots of polynomials, and it's called Descartes' rule of signs. And what it does is it tells you something about the types of roots you have. So what it says is if f of x is a polynomial with real number coefficients, now this is even more lenient than the rational root theorem. Real numbers means you could have irrational coefficients, so you could have square roots, stuff like that. Any real number coefficient, the number of positive roots that that polynomial will have is either equal to the number of sign changes you get in your function or less than that by an even number. And then the number of negative roots is equal to the number of sign changes in f of negative x or less by an even number. So what does that mean? I've got lots of examples to talk about what this means. So here's our first polynomial. We want to find the roots of this fourth degree polynomial. So we're trying to find out what numbers make this equal to 0. So part A, the number of positive roots, you simply count the sign changes, right? There's a positive here. So as I move along, I get one sign change here from positive to negative. That's still negative, and another sign change right here. So I saw two sign changes. So what that tells me is there are either 2 or 0 positive roots, right? It says it's equal to the number of sign changes or less by an even number. So there were 2 sign changes, and then if I subtract 2, which is the only even number I could subtract here, I either have 2 or 0 positive roots. Now to check for how many negative roots I have to plug in f of negative x. So if I replace all of these x's with negative x's, okay, if you take a negative x and raise it to the fourth, it's going to stay the same. But if you replace x with a negative x and cube it, that's going to make this term minus 2x cubed. Here, it's going to stay the same if I put a negative x. So that's going to stay as minus 9x squared. Here, if I replace that with negative x, I can combine it with that one. That's going to go positive 2x plus 8 equals 0. And then I count the sign changes that I get here. So I start with a positive. There's one sign change to negative, stays the same. Another sign change right there. So 2 sign changes means, again, I also have 2 or 0 negative roots. Now, it doesn't tell us the roots, it tells us how many. So now we're back to, okay, now let's try to find some of those roots. So we're back to the rational root theorem, where we're looking for if there are any rational roots, they have to be factors of p over q. Remember, p is all of the factors of your last coefficient, and your q is all of the factors of your leading coefficient. So we would have factors of 8 plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, divided by plus or minus 1, which is just going to leave us with plus or minus 1, 2, 4, and 8. So we'll just start trying. Let's start with 1, see if we get lucky. And remember, we're going to use synthetic division to see if we get, if this divides in, we should get a remainder of 0 if it's a factor. 8. Bring down the 1. 1 times 1 is 1. Add those, that's 3. -9 plus 3 is -6. -2 plus -6 is -8. 1 times -8 is -8. And hey, we lucked out. We get a remainder of 0. So what that tells us, remember, is a root is x equals 1. And of course, if sometimes you have to write these in factored form, that means the factor of this polynomial is x minus 1. And now we can work with this reduced polynomial. Remember, my reduced polynomial is x cubed plus 3x squared minus 6x minus 8. Now, this is where Descartes' rule of signs, I think, is very useful. we saw that there were either going to be 2 or 0 positive roots. We found a positive root, 1. So what does that mean? That means there can no longer be 0. That means there has to be another positive root. There has to be another positive root because we have either 2 or 0. So we could try 1 again. And you can do the synthetic division, or you could see if you plug in 1 here, are you going to get 0? Well, that's going to be 1 plus 3 is 4. 4 minus 6 is negative 2 minus 8. So 1 is not going to work again. So let's pick it up with 2. 1, 3, negative 6, negative 8. 1, this is 2, 5, 10. Negative 6 plus 10 is 4. That's positive 8. And we get a remainder of 0. So we know that x equals 2 is a root, which means a factor is x minus 2 is our factor. So now we know we've got 2 positive roots. That's all for positive roots. So we know the other 2 have to be negative. Now we don't need to guess anymore because our reduced polynomial is a quadratic. It's x squared plus 5x plus 4, which we know would factor into x plus 1, x plus 4. So I get 2 more roots, and as promised, they were either going to be 2 negative roots or 0 negative roots, and in this case, we have 2 negative roots. So that means, just to summarize this, my polynomial could be factored into, might as well start with these, x plus 1, x plus 4, x minus 2, x minus 1, and of course the roots are x equals negative 1, negative 4, positive 2, positive 1. Okay, let's look at another one. So we'll start by trying to see if we can determine how many positive roots we have. So we look at the sign changes. There's 1 sign change, 2, 3, 4 sign changes. So that means we could either have 4, 2, or 0 positive roots, right? 4 sign changes or less by an even number. Then we'll look at f of negative x. If I replace all of these x's with negative x, that will stay positive. Negative x here cubed would make that a negative, so that'll combine with that negative to make that positive. That's going to stay the same. Negative x here will make that positive. So there's f of negative x. And notice there aren't any sign changes, right? These are all positive terms. So what Descartes' rule of signs would tell us is that there are 0 negative roots. 0. There's no sign changes. No sign changes. Now that's useful then, because if I'm going to then start to tackle trying to find these roots with my P over Q, which normally rational root theorem, we'd take all of your roots of positive 16 plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, and divide by all of the factors of 1, which are plus or minus 1. But we know since there's no negative roots, we don't have to worry about any of the negatives. The only possible rational factors are going to be positive 1, positive 2, positive 4, positive 8, and positive 16. So it takes out half of my cases that I need to check. So that's pretty useful. We'll start with 1. Bring that down. That's 1, 1, negative 7, 17. Negative 32 plus 17 is negative 15. Oh, close. 16 minus 15 is 1 though. So, but that's not a root then. I need to get 0. So we can cross 1 off our list. Let's try 2. 1, -8, -24, -32, 16. 1, 2, -6, -12, -36. No. This should have been +24. There we go. That's 12, huh? 2 times 12 is 24. -32 plus 24 is -8. It gives me -16 and a remainder of 0. So I know that x equals 2 is a root. And x minus 2 is a factor. All right, so now we can work with our reduced polynomial, which is now x cubed minus 6x squared plus 12x minus 8. And remember that 2 could be a double root, right? It could be go into this again. So let's try that again. So 1, -6, 12, -8. -4, -8, +4, 8, and I get 0. So once again, 2 is a root, x minus 2 is a factor, and now I can look at my reduced polynomial, which is now a quadratic, and just factor this. That factors into x minus 2 times x minus 2, which means, okay, so what this tells me is now that means my original function factors into all of my only roots were 2, and all of my factors are x minus 2. So this means it really factors into x minus 2 4 times x minus 2, which means it's x minus 2 to the 4th. So my root, my one and only root, is x equals 2. But now how does that work with Descartes' rule of signs? Because we saw that there were going to be 4, 2, or 0. You could argue that x equals 2 is only one positive root, which would not fit Descartes' rule of signs. But if we count the multiplicity of that root, then we could also make the argument that there were 4 roots. They just all happen to be 2. And that's the way we're going to think of it. So x equals 2, and we can add the note here that I have a multiplicity of 4. So we're going to count that as 4 positive roots. They just all happen to be the same. All right. So that's one thing about Descartes' rule of signs, is multiplicity counts when we're talking about the number of roots. All right, so let's look at this one. This is now just a cubic equation. Number of sign changes in f of x is 1, 2 sign changes. So again, we have 2 or 0 positive roots. F of negative x is going to be negative x cubed minus 5x squared. Put in negative x there, that'll make that minus 5x plus 3. So looking at the sign changes here, we see there's only one sign change, so we only have one negative root. So if you subtract 2 from that, you're going to get -1. So there has to be one negative root of this thing. If it's a rational root, then it would have to be factors of plus or minus the factors of 3, 1, 3, divided by plus or minus the factors of your leading coefficient, which is 1. So this is just plus or minus 1, plus or minus 3. There's only 4 things to check if we have rational roots here. So we could try 1. That's not going to work. We're going to get a remainder of 4 here. So that's out. Let's try 3. One, 3, negative 2, negative 6, negative 1, negative 3, and I get a remainder of 0. Okay, so then we know we have a root of x equals 3. Of course, the factor then is x minus 3. And we're down to a quadratic, x squared minus 2x minus 1. And notice this doesn't factor. So if it doesn't factor, what's our backup is to use the quadratic formula. X equals, here, we'll write the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Remember, your a is your coefficient of x squared, your b is the coefficient of x, so b is negative 2, and that's your c. So we're going to have the negative of negative 2, negative b, plus or minus the square root of b squared, minus 4 times a times c over 2a. If we reduce that, that's positive 2 plus or minus, that's going to be 4 plus 4. The two negatives make that plus. So that's the square root of 8 over 2, which is really 2 plus or minus. Remember, 8 is 4 times 2. The 4 can come out as a 2. So that's 2 root 2 over 2. And I can split this up. If I divide this and then this, that gives me 2 over 2 is 1, plus or minus, cancel the 2's here, plus or minus root 2. Those are my other two roots. So to summarize here, I have roots of x equals 3, 1 plus root 2, 1 minus root 2. Let's see how that works with Descartes' rule of signs. These two are positive, so I do have two positive roots, and as promised, there's our one negative root, right? We could either have 2 or 0 positive roots and 1 negative root. So they don't have to factor nicely to still fit with Descartes' rule of signs. As far as the factored form, you can still write this in factored form. This original function factors into x minus 3, x minus quantity 1 plus root 2, and x minus quantity 1 minus root 2. Think about it, if you set this equal to 0 and solve each of these, you're going to get those three answers. So it looks funny, but you can still write that in factored form. All right, one more. This will be our challenge one here. This one's a 5th degree polynomial. And this would be a good time if you think you've got this down, maybe pause the video and try to use Descartes' rule of signs to determine the number of roots and then try to actually find them. All right, so assuming you've tried that, let's check. So our original function has 1, 2, 3 sign changes. So we have 3 or 1 positive roots. F of negative x. So you've seen what happens. Anytime you plug a negative x into an odd power, it's going to change the sign. That's going to be minus x to the 5th. But if you plug it into an even power, it's going to stay the same. That's going to be a negative, which is already a negative. So that'll be positive x cubed. That'll stay the same. That's going to change that to minus. So that'll be positive 20x minus 24. So I have 1 sign change, positive, positive. I have 2 sign changes. So that means I have either 2 or 0 negative roots. Okay, we do our P over Q. There's a lot of them because I have to think about all of the factors of negative 24 plus or minus 1 plus or minus 2 plus or minus 3 plus or minus 4 plus or minus 6 plus or minus 8 plus or minus 12 plus or minus 24. Fortunately, all of those only divided by the factors of 1 plus or minus 1, my leading coefficient. All right, well, let's get into this. So if we try 1, that's what I would do, start with the simplest. One, 3, 2, 4, negative 16. I'm not going to get a remainder of 0. So I know this isn't going to work. I get negative 40. Okay, so 1 is not a root. So let's move on to, I like to try, I mean, you could try negative 1. I'm going to maybe try a few more of the positives before I go. I definitely don't want to try these big numbers if I can help it. So I would maybe try a few of the positives. And if I don't get anything, then try some of the lower negatives. One, 2, 4, 8, that's at 7, 14, that is 16, 32, negative 12 plus 32 is 12. Good, this is 24. So I get a remainder of 0. So then I know x equals 2 is a root, and my factor is x minus 2. Now there's something to learn here. There's something to learn here. If I look at my reduced polynomial, right, notice, and this would be x, this would be a 4th degree, x to the 4th plus 4x cubed plus 7x squared plus 16x plus 12. Notice that there are no sign changes here, right? There are no sign changes. It's all positive throughout here. So because there's no sign changes, what does that tell me? That tells me there are no more positive roots. No more positive roots, right? If 2 is a root, and remember Descartes' rule of signs said we had either 3 or 1 positive roots. We got our 1 positive root, and then we've now determined that is it. It can't be 3 positive roots. Otherwise, we would have seen some sign changes here, right? So why is that useful? Now I know I don't need to bother checking any more of these positive numbers, right? I can stop at 2. So now I could go to working with negative numbers because we know there's either 2 or 0. So maybe we try negative 1. And I'm going to work with the reduced polynomial. 1, 4, 7, 16, 12. Negative 12. Perfect. I get a remainder of 0. So we have x equals negative 1 as a root. And my reduced polynomial is now 1x cubed plus 3x squared plus 4x plus 12. Again, notice it's all positive. So that's again tells me there's no positive roots, but we already knew that from before. Now we can keep going, right? We could keep checking negative numbers, but I want to remind you that oftentimes, not always, but if you get down to a cubic, you might be able to just factor this by grouping. And so you start to look at, like, if I group the first 2 terms and the last 2 terms, notice that here I could factor out an x squared, and that gives me x plus 3. And here I get take out a 4, gives me an x plus 3. And between these 2 terms, I can factor out an x plus 3, leaving me with x squared plus 4. So now this is just with the reduced polynomial, but let's see what roots I have. Well, certainly I get x equals negative 3. There's another root, another negative root. And remember, so we had x equals negative 1 and x equals negative 3, and Descartes' rule of signs predicted that we would either get 2 or 0. So we have 2 negative roots. one positive root. Now, what's going on with this last factor? If I try to set that equal to 0, we can't do that, right? There are no real solutions to that. No real solutions. In your class, you might start to get into imaginary numbers where we can talk about an imaginary solution, the square root of -4. For right now, though, we're only talking about real solutions, so there aren't any. All right, so to summarize here, the roots of my equation were x equals 2, -1, -3, and my function factors into x -2, x plus 1, x plus 3. And then, yeah, we just leave it like that. X squared plus 4 is doesn't really factor anymore. Okay, so hopefully finding zeros of polynomials can now become a little bit easier now that you have Descartes' rule of signs to help you to determine the number of positive and negative roots you can expect to find.